in USA.
The history of waves goes back to the ancient Greeks. They discovered the connection between waves and sound. Robert Boyle proved that sound cannot travel through a vacuum. This is a drawing of what his experiment looked like. Isaac Newton described mathematically and scientifically how sound travels. This was very significant. In 1942, Dr. Carl Dusek was the first person to use sound waves for medical purposes. Since then, ultrasound has come a long way. In 1951, 2D B mode was produced. In 1966, Doppler was first produced. And then all the way in 1991, 3D ultrasound was first produced.
Okay, so we can classify waves into electromagnetic, which transfer energy without a medium, and mechanical, which require a medium to transfer energy. There are some examples of both types listed down below. You can also classify them into transverse and longitudinal. So transverse waves, particles move perpendicular to wave propagation, and in longitudinal waves, particles move parallel to the direction of wave propagation. Here's a little visual of how transverse waves move. So the particles are oscillating. And then here is a visual of longitudinal waves. So the particles are going to vibrate back and forth and in the same direction as wave propagation. And then ultrasound is a longitudinal mechanical wave. So sound wave frequencies range from 20 hertz to over 12 million hertz. Infrasound is less than 20 hertz. It's used by animals like giraffes, elephants, and whales. We also have audible sound, which is the sound we hear daily. It's from 20 to 20,000 hertz. Then we have ultrasound, which is a high frequency sound wave. This is going to be greater than 20,000 hertz, and it's used by animals like bats, grasshoppers, frogs, and mice. And then we have diagnostic ultrasound, which is important to us, and it's going to be from 2 to 12 megahertz.
So let's go to some fundamental information about the waves. First, the amplitude. It is the maximum magnitude of the displacement as shown in the picture. The wavelength is the length of the whole cycle. The period is the time it takes for the whole cycle to complete. And the frequency is the number of cycles per second. Next, we're going to dive into some of the acoustic variables that we will discuss. We learned before. They are pressure, density, temperature, and particle motions. First, pressure. It is a concentration of force. It varies as the wave propagates through the medium. It is a maximum during compression and a minimum during rarefaction. Most common units are millimeter mercury, pascals, kilogram per meter squared. Next is the density. It is a different medium different mediums have different densities. The density equals mass divided by volume. At the compression part, the density is the maximum, and the rarefaction part, it is the lowest. Next is the temperature. As the temperature increases, the particle motion will also increase. So the sound will travel faster through the medium. The last one is the particle motion. As the sound wave travels through the medium, the particle oscillates. This allows the transfer of the ultrasound. Yeah, so why are ultrasound so important to us? Because the ultrasound can use high frequency sound waves to create an image or treat diseases. Ultrasound can be divided into two categories. First is the therapeutic ultrasound. It can provide heating to the soft tissues in the body so that can help heal the disease. Typical frequencies for therapeutic ultrasound is 0.5 MHz to 3 MHz. The other is diagnostic ultrasound, which we are doing now. It's a diagnostic imaging technique based on the application of ultrasound. It can create an image. It also includes different modes such as A mode, B mode, M mode. The typical frequency is from 2 megahertz to 12 megahertz.
Next is how ultrasound waves create an image on the screen. The longitudinal waves we send out into the tissue from the ultrasound transducer are sent out in pulses. These pulses then hit structures in the body and react to them. When the waves react with structures, they will be absorbed, reflected, transmitted, or a combination of them. Depending on the kind of wave we receive back from reflected surfaces and the time it took to receive the reflected wave will determine how the image will appear on the screen. If we receive no reflected wave at all, then that area of the image will look black because the brightness of the image is determined by the amplitude of the returning wave. Depending on the density of the tissue you are imaging, you will receive different propagation velocities. A faster velocity will make your tissue appear higher on the screen because the reflection of your wave reached the transducer faster than the tissue with the lower propagation velocity. This same theory will apply to tissues that lay more superficial. The closer the tissue is to the transducer, the sooner you will receive the reflected wave, and the structure will be created in your image higher than the tissues that lie below it. Here are some examples of propagation velocities of mediums you may be encountering in ultrasound while trying to produce an image. Understanding how fast your wave travels through these mediums will help you understand how your image will look. There are many different imaging modes we use in ultrasound, like A mode, B mode, and M mode. Here's an example of an M mode and a B mode image. Here's a graph of the displacement of one particle as a function of time. Another visualization of longitudinal waves. And here's the last image of a longitudinal wave.